Assalamu alaikum warahmatullahi ta'ala wabarakatuh. I am Salma Al-Mahdi and today we are going to discuss heme metabolism. Our objectives include revising the structure of heme, outlining the steps of heme synthesis and degradation while highlighting key enzymes and key intermediates, to discuss regulation of heme synthesis, discuss transport and excretion of bilirubin and its conversion into bile pigments, and to discuss relevant disorders, particularly porphyrias in relation to heme synthesis and jaundice in relation to heme degradation. Porphyrins and bile pigments are discussed together because heme is synthesized from porphyrins and iron, and it's also degraded into bile pigments and iron. So it is more convenient to discuss them together. The site of synthesis of heme regarding to cells, it occurs in most mammalian cells. So almost or the majority of cells in the body can synthesize heme except mature RBCs. However, immature RBCs or early precursors of RBCs, known as erythroid precursors, in the bone marrow synthesize up to 85% of heme, and this makes sense because heme is part of hemoprotein, which is the main package of the RBCs. Heme synthesis also occurs in hepatocytes, which accounts for the majority of the remainder of the 15%. At the subcellular level, heme synthesis occurs in both the mitochondria and the cytosol. The first step of ALA synthesis, we will shortly know what is meant by ALA. It occurs in the mitochondrial matrix. Subsequent steps occur in the cytosol, particularly porphyrin intermediates formation, and then again in the mitochondrial inner membrane, the final steps, particularly where ion is inserted into the final product or the final intermediates of heme synthesis, so porphyrin 9. This occurs again in the mitochondria. This compartmentalization is very important, particularly to regulate heme biosynthesis and to prevent accumulation of toxic intermediates. What do we mean by porphyrins? Porphyrins are cyclic compounds formed by linking 4 biroll rings through methynyl bridges. They form complexes with metal ions such as heme, and the ion or the heme will be linked to the N atom of the biroll ring. As you know, ferrous ferric ion in its both forms is present at the center of the heme compound. Iron porphyrins that contain iron, of course, the examples are heme of hemoproteins and, of course, also myoglobin, and magnesium containing porphyrins occur in chlorophyll in plants. Porphyrins are colored and they have the ability to fluoresce, giving red color. And this is a biroll ring, and this is porphyrin, and this is Fischer representation of porphyrin or porphyrin. Hemoproteins in general play important functions. For example, you have already discussed hemoglobin role in transporting oxygen in the blood to reach extrapulmonary tissues, role of myoglobin in storing oxygen for muscle use, cytochrome C in the electron transport chain, cytochrome P450 will be discussed today in a different lecture regarding symbiotic metabolism, catalase in degradation of hydrogen peroxide or detoxification of hydrogen peroxide, and tryptophan pyrrolase in oxidation of tryptophan. The first step of heme synthesis is condensation of succinyl-CoA, which is considered active succinate because of the presence of CoA, and the amino acid glycine. They will be condensed together or compound together, catalyzed by ALA synthase with the release of CoA and thiol, and the coenzyme here is pyridoxal phosphate. Pyridoxal phosphate, as you remember, is a coenzyme for ALA synthase as well as transaminases. The product here is alpha amino beta ketoadipate or ketoadipic acid, which will be decarboxylated by the same enzyme, leading to the formation of alpha amino levulinate or amino levulinic acid or ALA. The third step is condensation of two molecules of ALA or amino levulinate by ALA dehydratase with the release of water, and the product here is porphyrinogen. Is the first precursor pyrrole. As you can see, the first pyrrole ring has been formed. The fourth reaction is deamination reaction by a deaminase, also known as uroporphyrogen 1 synthase, where the four molecules of porphyrinogen leading to the formation of hydroxy methylbilane, which is a linear tetrapyrrole. And then this linear tetrapyrrole is either spontaneously cyclized to form type 1 uroporphyrogen, or under the influence of uroporphyrogen 3 synthase will lead to formation of type 3 uroporphyrogen. Under the influence of decarboxylase will lead to formation of coproporphyrogen 3. Coproporphyrogen 3 pion oxidase will lead to formation of orthoporphyrogen 3. Then by another oxidase will lead to formation of protoporphyrin 3, and then ferrochelatase is the enzyme that is responsible for incorporating or adding ion in the last step to form mature heme. All of these steps are mitochondrial steps, particularly in the mitochondrial membrane. How is heme synthesis regulated? As a step of ALA synthase or alpha aminolevulinic acid synthase catalyzes the rate limiting step of heme synthesis. It is subject to repression and de-repression, both of them by heme. In the presence of heme, the rate of synthesis of the enzyme itself decreases, and this is called repression. And in the absence of heme, the rate of synthesis of ALA synthase increases, which is de-repression or relieving the repression. Many drugs can increase the rate of hepatic ALA synthase, such as barbiturates and as antifungal griseobalvin. Porphyrinogens versus porphyrins. All porphyrinogens, pay attention here to the suffix gene. Porphyrinogens are colorless because they lack the conjugate bonds. So the conjugate bonds are responsible for giving color or fluorescing. Porphyrins ending in IN are colored and they fluoresce. When porphyrins are present in urine or feces, they can be extracted by appropriate solvents measured by either spectrophotometry or colorimetry. Both of them are analytical methods that depend on Lambert law, where the solute is measured depending on its concentration and the wavelengths detected by a spectrophotometer or colorimeter in the lab. Why do we need to measure these compounds? Clinically wise or biochemically wise to diagnose conditions known as porphyrias. And this is a graph showing the absorption spectrum of hematoporphyrin using spectrophotometry. Porphyrias are genetic or acquired disorders of heme synthesis. They are rare, particularly the genetic forms of porphyrias, but they should be considered in the differential diagnosis of any abdominal pain and neuropsychiatric disorders. Accumulation of metabolites that are toxic to the abdominal nerves and central nervous systems. Porphyrias can also manifest as skin or cutaneous presentation in the form of photosensitivity and disfigurement. And this diagram here shows you the biochemistry of the major symptoms and signs of porphyrias, particularly the genetic or the inherited forms, where mutation in the DNA will lead to abnormalities in the enzymes that are responsible for heme synthesis. When there is accumulation of ALA and porphyrin gene, PPG, and or decrease in heme in cells and body fluids, this will lead to neuropsychiatric symptoms and signs. While accumulation of porphyrin genes in the skin and tissues will lead to spontaneous oxidation of these compounds, which will lead to photosensitivity in reaction to light. For example, such as sunlight falling on the skin. Porphyrias are classified depending on the site of accumulation. If it is hepatic porphyrias, liver is affected, causing neurovisceral symptoms. So they will present with abdominal pain, for example. Erythropoietic porphyrias, where accumulation of metabolites occur in the bone marrow, causing cutaneous symptoms. Clinical presentation either acute or cutaneous, acute neurovisceral attacks or abdominal pain, including abdominal pain, cutaneous porphyrias, whereas presentation is mainly skin photosensitivity. And this is to show you the acute neurovisceral porphyrias and affected enzymes in addition to the key features. This is the cutaneous porphyrias. The famous one is porphyria cutanea tarda, and their defective enzymes and key features. How is heme catabolized in the body? Under physiologic conditions, an adult human weighing 70 kilograms destroys around 1 to 2 per 10 to 8 RBCs per hour. This is a huge number of RBCs being destructed, releasing their hemoglobin. An adult turns around 6 grams of hemoglobin per day. So we are going to deal with hemoglobin and with its heme content. Breakdown of hemoglobin produces the globin, also protein part, which is degraded to this constituent amino acid, and we have already discussed how amino acids are catabolized in the body. Iron enters the iron pool of the body. The porphyrin part will be degraded to bilirubin. Heme catabolism occurs in the liver, in the spleen, and in the bone marrow by a microsomal system called heme oxygenase. Heme-derived iron reaches heme oxygenase in a ferric state. Here, ferric state, it will be reduced and then oxidized again to ferric, and then iron will be released to be reutilized or joining the iron pool, and the product is called biliverdin. As you can see, it is a linear compound. The pyrroles are there, but it's no longer acyclic, and iron is lost. So this biliverdin can be reduced to bilirubin. As you can see, they are quite similar. However, bilirubin is the reduced form. You can see the two hydrogens here coming from NADH compared to the biliverdin. Another difference is that biliverdin is green while bilirubin is yellow. 1 gram of hemoglobin yields 35 milligrams of bilirubin. In a normal adult, 200 to 350 milligrams of bilirubin is produced daily, mainly from hemoglobin, also from ineffective erythropoiesis, as well as other hemoproteins such as cytochrome or other heme-containing proteins. The problem is that bilirubin is non-polar, so it's a problem to transport it in the aqueous environment of blood, and it has a tendency to accumulate and to bind to lipids. In the blood, bilirubin will be transported by albumin from the peripheral tissues. It will be transported to the liver, where the liver deals with it, as we are going to see. Some drugs displace bilirubin from albumin. Examples of these drugs include sulfonamides, antibiotics, non-steroidal anti-inflammatory drugs such as ibuprofen. They will displace albumin from bilirubin from its site of transport in the albumin, and they have clinical consequences in causing increased level of bilirubin in the blood, which is known as hyperbilirubinemia, and in the neonates it is known as kernicterus. As conjugated bilirubin, that's bilirubin linked to albumin, it reaches the terminal linked to glucuronidase, glucuronides, for example. The conjugated bilirubin is conjugated to glucuronides. It reaches the large intestine and it is acted upon by bacteria. Bacterial glucuronidase will remove the glucuronide conjugate from bilirubin, and now bilirubin is unconjugated. It will be reduced to urobilinogen, which is still colorless. A small part of this urobilinogen will be reabsorbed again from the cavity of the intestine to the back to the blood, similar to the enterohepatic circulation that we have discussed when we talked about bile acids. So this urobilinogen in the blood can find its way to the urine, and it will be excreted in urine as urobilinogen. However, most of the urobilinogen will stay within the intestine. It will be oxidized to urobilins, which will be excreted in feces. And that is why when we want to test one of the tests that assess the general condition of the body, and particularly regarding heme metabolism, is we test blood and urine for the catabolites of heme, because a small part, as we said, is excreted in urine, the majority will be excreted in feces. We said heme catabolites reaches the liver. Liver will uptake the products using hepatic parenchymal cells by a large capacity facilitated transport. And this is one of the major roles of the liver regarding metabolism. And after uptake to the inside of the cell, intracellularly, there is again conjugation of in the smooth endoplasmic reticulum with glucuronic acid, which increases its polarity. Presence of glucuronic acid with bilirubin will make it more polar, and this conjugation is the responsibility of glucuronyl transferase enzyme. And then conjugated bilirubin will be secreted into bile by active transport, a rate limiting step, as bilirubin diglucuronide reach the intestine, where it will be mostly excreted as urobilin. Some of it, as we already mentioned, can join the circulation to be later on excreted in urine. Biomedical wise, we are going to discuss jaundice as a relevant disorder of heme metabolism. Both of these are disorders of heme synthesis, while jaundice is a disorder of heme metabolism. What is jaundice? Is elevated bilirubin in plasma or blood, hyperbilirubinemia, due to either overproduction or failure of excretion. We have conjugated bilirubin, as we have already mentioned, versus unconjugated bilirubin. So the hyperbilirubinemia would be either conjugated hyperbilirubinemia when we test the blood, for example, or the urine, we will find conjugated bilirubin. Or it could be unconjugated hyperbilirubinemia due to the presence of unconjugated bilirubin, or could be a mixture of both. Unconjugated usually result from hemolytic anemias. So the rise in bilirubin is due to overproduction due to breakdown or destruction of the RBCs due to different conditions that can lead to hemolytic anemias before in the early step of hemoglobin breakdown. So the disorder here is related to an incident that is before bilirubin is produced or it reaches the liver for conjugation. A famous example is in neonates, because they are immature. Even if they are mature, they have relatively higher content of RBCs. Some of these RBCs will be destructive, and these children in the early days, first or second day of their lives, they will present with neonatal, what is called physiologic jaundice. Another disorder is Crigler-Najjar syndrome 1 and 2, which are due to defective conjugation. Gilbert syndrome is also a result of defective conjugation. And conjugation could also be toxin-induced or due to hepatitis. The liver is inflamed and it cannot perform its function or its role in conjugated bilirubin. All of these conditions result in the increase of unconjugated bilirubin or unconjugated hyperbilirubinemia. The jaundice can result from a rise or an increase in bilirubin after conjugation due to obstructive or cholestatic conditions, which result from lack of hepatic common bile duct, because bilirubin will be stored in bile and will be released when the bile is released, for example, following a lipid or containing meal into um, the bile duct. Dobbin-Johnson syndrome is due to defective hepatic excretion of bilirubin. Rotor syndrome is defective hepatic storage or excretion of bilirubin. Hepatitis itself can also result in conjugated forms of hyperbilirubinemia. Jaundice, clinically, it needs to exceed a certain concentration to be appreciated as a visible or a sign. And particularly, we look for it as yellowish discoloration of the sclera or of mucous membranes. You can look up pictures of jaundice in the internet. It is quite obvious or clear. It will be more clear for you. Jaundice can be classified into prehepatic, hepatic, or post-hepatic. Prehepatic, the condition is before bilirubin reaches the liver. Hepatic is when the disorder is due to a hepatic condition. Post-hepatic is after bilirubin is being conjugated into the liver. Prehepatic is excessive amount is present of bilirubin is presented to the liver, and the example here is excessive hemolysis, as in hemolytic anemias. The hepatic jaundice will result from impaired cellular uptake, for example, defective conjugation, or abnormal secretion of bilirubin by liver cells. So any of these conditions can lead to hepatic jaundice. The post-hepatic jaundice is due to impaired excretion, due, for example, to the mechanical obstruction. For example, if there is gallstones or a malignancy that affected as a flow of bile from the bile duct. And here is a table that shows the type of jaundice, whether it is prehepatic, hepatic, or post-hepatic, and the type of bilirubin in prehepatic will be unconjugated because it has not yet reached the liver for conjugation, while in post-hepatic it is already conjugated. In the hepatic, it is a mixture of both. The serum bilirubin will be indirect, when we say indirect, we refer to the unconjugated bilirubin. When we say direct bilirubin, we refer to the conjugated bilirubin. So the test, the laboratory test for prehepatic jaundice, the indirect bilirubin will be high, and the test in the post-hepatic, the direct bilirubin will be high, and in the hepatic, of course, it will be a mixture. Prehepatic is unconjugated, so it is not expected to be conjugated, and Of course, it will not find its way into bile, so both of them will be absent, but urobilinogen will be quite high. In contrast, in the post-hepatic, conjugated with bilirubin will be high, bile salts will be detected, or bile bilirubin will be detected, while urobilinogen will be absent or very trace amount, because it is not, most of it will be lost in feces. The urine color will be normal in prehepatic because it is not found its way into urine, and post-hepatic will be dark, and the hepatic will be also dark due to the presence of the conjugated bilirubin, which can't find its way into the circulation to be excreted in urine. What happens to stool? We said the bilirubin can be excreted in both urine, but mainly in stool. In stool, in the perihepatic jaundice, the stool will be dark because unconjugated will be mostly in the intestine, and it will be excreted via feces. The post-hepatic, the color will be less dark compared to the prehepatic because this is this conjugated type of bilirubin. What happens to the liver enzymes in jaundice? AST and ALT, the aminotransferases, will be normal in prehepatic because the liver is not involved. But in the hepatic, it is expected to have high levels of these enzymes because if there is, for example, hepatitis, it will destroy hepatocytes, leading to release of these enzymes. In post-hepatic, they can be increased as well. However, mostly the increase will be in alkaline phosphatase levels because alkaline phosphatase is mostly related to obstructive hepatic conditions because of the anatomical position of the enzyme itself. This concludes our talk. Thank you very much.